Welcome back, everyone. Today we're going to learn the second class of dimensional reduction. And for that, firstly, we're going to learn Fisher discriminant analysis. So for Fisher discriminant analysis, we're going to cover a dimensional reduction with the label. So we're going to cover the contents of dimensional reduction with label information. So the ultimate goal is maybe classification and regression. We know that when we have label information, we can use those data for classification and regression. So here we're gonna first reduce the dimension, and the ultimate goal would be a classification and regression. So the difference between the dimensional reduction with label, last time we have learned the PCA, principal component analysis, and here we ignore label information even if it's available. So even if it's available, we just ignore the label information and just reduce the dimensional reduction. So only choose directions of maximum variance, so we just ignore any label. On the other hand, Fisher discriminant analysis takes into account the label information. So we consider label informations, and also for the case of Fisher discriminant analysis, it is also called a linear discriminant analysis. So FDA and LDA are just exactly the same but different names, so don't be confused. So maybe someone will call this algorithm as Fisher discriminant analysis, and others maybe call it as a linear discriminant analysis. Anyway, both are the same. So both FDA or LDA projects data. So the important is FDA and LDA projects data while preserving class separation. So because we know the label information, we just preserve class separation. So examples from same classes are put closely together by the projection, and examples from different classes are placed far apart by the projection. So that is our ultimate goal, how to do a FDA or LDA. And let me explain the FDA in a graphical way. So here, let's say we have data with labeled green one and the red one. And our goal for FDA is projecting these data so that we can reduce dimension from these 2D to 1D. So our goal is finding the one-dimensional line so that we can project these data. And let's say in this case we have two classes, and if you say we have projecting line like this, then this original data for the green one and the red one will be projected like this. And if we set our projecting line like this, if we project this original data onto this line, we will also get these two lines. And if we set this line, then our projecting data will be represented like this. Then among these examples, how can we determine which one is the best and which one is the worst? And here, as you can see, in this line, these two data are rarely overlapped, right? So here, this one is maximally separated. We can say this one is maximally separated. On the other hand, by projecting original data onto this line, we have the distribution like this for the both green one and the red one. So we can see most data are mostly overlapped. And as we said, our ultimate goal is maybe classification or regression after dimensional reduction. So here, if we have two set of data like this, we can classify these two data with the class 0 and class 1. However, if we only have these data, we cannot distinguish the red one and the green one. So this is not the good case, right? So this one would be the worst, and this one is the best. So based on this, our goal is finding the ultimate line that preserves the class data. So that means we need to preserve data that can be. We need to find the ultimate line that maximally separates data maximally. Then the question is, how can you find the proper projection line that maximally separate those original data? So for that, linear regression projects is data point. So here, let's assume zero mean, and in the previous lecture, we have learned how to make the data to zero mean. So if you don't have the data with zero mean, then you may shift the data by subtracting its mean. So by doing so, you can make the original data with a zero mean. So here, as we know that the projection onto line omega is just nothing but the inner product of the omega and x. So the inner product of omega x is just written as omega transpose x, or omega 1 x1 plus omega 2 x2. So here we assume that omega 0 is equal to 0. And the problem is, we need to find the dimensional reduction. So from these two-dimensional data, so we have x1 and x2. Our goal is reducing dimension. So that means we're gonna have a one-dimensional data, or y hat is equal to y hat is just the scalar value. So for each data set is gonna be projected onto omega. So projected length on omega direction. And for a given omega, distribution of the projected points is gonna be specified. And our remaining question is, which omega is better for classification? And from the previous slide, in graphical ways, we are knowing that omega that separates original value with minimum overlap, or maximally separate data, is the best. Then the question is, how can you find that? And to calculate the line omega, we need to consider a sample statistics in projected space. So so let's say for data we have two classes, class C0 and class C1, and the data we're gonna be projected on the line omega, and we're gonna consider sample statistics in projected space. So let's say for the class C0, let's say we have sample mean mu0 and sample variance S0. Then the sample mean and sample variance can be calculated like this, as we learned in the last lecture. And these original data will gonna be projected onto line omega, and in the projected space, the mean value is gonna be just the inner product of mu0 and omega, and the sample variance is omega transpose S0 omega, as we learned in the PCA class. So this one is just a sample mean mean, and variance in the projective space, not the original space. So it's the projective space omega. So this one is what we have learned in the last time. And similarly, for the data in the class C1 is also working as the same. So this one in the projective space, this one is also the same, omega 1, the inner product omega 1 and omega mu 1 and omega transpose S1 omega. So from this statistics, let's do some Fisher discriminant analysis. So our goal is find omega, so that when the projected onto omega, the classes should be maximally separated. That means a maximized distance between classes, and each class should be tight. So that means minimize class of each class. So that is between classes that should be maximally separated, and within classes it should have a minimum variance. So for that, to have maximized distance between classes, we need to have maximum mu 0 transpose omega minus mu 1 transpose omega square. So this one is the mean of the class 0, and this one is the mean of the class 1. So by finding the maximum distance between these two minimums, these two average, we can find the maximum distance between classes. And for the second condition, we need to find each class should be tight, and this one can be calculated by minimizing variance of each class. So here, minimum n0 omega transpose S0 omega plus n1 omega transpose let's see, S1 omega. So here, n1 and n0 and n1 just indicates the number of data in the class in C0 and C1. So N0 is the number of data in the C1, and N1 is the number of data in class C1. So here, if we have more data, then it will have more weight. It can be considered like that. So at the same time, we need to. So our goal is finding the omega that satisfies these two conditions at the same time. So for that, we have one maximization problem and one minimization problem. So to combine these two at the same time, maybe we can rewrite the objective function like this. So let's use this one. So for that, we can rewrite these conditions by considering both two cases. So here, if we want to maximize this first condition, we can rewrite maximizing separation of a projected means square, and by minimizing this data, we can use it in the denominator. So by dividing these into the denominator, sum of within class variance, so you can rewrite this. The final our objective function can be like this. So this one is here, and this one is here. So by using this, we can find the omega by satisfying these two conditions at the same time. So here, this case is small separation. So when you see this, you can see the some amount of range are overlapped, but in this case, by setting the omega like this, you can find these two data are not overlapped. And also within the class, this data is mostly separated, but in this case, the data are well tightened. So from that, we can say that this one, this case is the better separation. So we can say this omega is the good line. So from that, let me rewrite this our objective function like this. So our objective is finding the omega that maximizing this equation. So if we as we know that n0 and n1 is just nothing but the number of data. So these values are scalar. So by rewriting this, we can rewrite this the denominator as omega transpose n0 as 0 plus n1 as 1 plus omega. And if we define m is equal to mu0 mu1 and sigma is just n0 s1 s0 plus n1 s1 and mu is equal to r omega. This is just the definition. Let's define these values for the simplicity. Then our objective function j omega can be simplified like this. So in our objective function, when we also rewrite this by using this definition, so here from u is r omega. So omega is nothing but the r inverse u. So by rewriting this, our objective function can be written like this. And finally, by rewriting our objective function is nothing but r inverse transpose m transpose the u. Let's say here u hat is equal to the unit vector of the u. So this one is our objective function. So our objective function is actually maximizing this function. So from that, so we can see that, and this one is maximized when u is equal to a times r inverse transpose m. So here this can be understood like this. So the objective function is nothing but the inner product of r minus t m times u hat, and we know that from the definition of the by definition the inner product is maximized when the two vectors are parallel, right? Because in the inner product we combine the magnitude of the inner product can be calculated like this, and this one is maximized when the cosine theta is equal to pi over 2. And when the cosine theta is cosine theta is equal to 1, so this one is maximized when the theta is 0. So that means two vectors a and b should be parallel. So that means to be maximized this objective function, these two vectors should be rewritten as two parallel vector, and from that we can rewrite u should be some value you should be parallel this, so that is the scalar multiplication. So u should be parallel with r minus t m. Yeah, so let me summarize these previous results. So we have discussed about dot product of unit vector and another vector is maximum when the two have the same direction or they are in parallel. So from that we know that u vector should be some you should be u vector should be in parallel with r minus t m. So from that we can rewrite by using the definition that we defined earlier. We can rewrite this. So, and from that our ultimate goal is finding the projective space omega. So from that let's go back to the omega. So from these equation, our goal is finding the omega that maximally separate the two classes at the same time, and at the same time the minimizing the variance within the class. So this one is our the final form of the omega. So our goal is finding the omega that satisfies this condition. So based on that, let's implement this Fisher discriminant analysis in Python code. So for that, let's first generate some data set. So from that, let's see this. We have data with label. So the class C1, C0, and C1. So for that, let's first randomly generate some multivariable normal vectors. So x1, x0, and x1. And let's see this x0 and x1. And for that, let's calculate the sample mean and sample variance. So for that, let's calculate the sample mean and sample variance like this. And if we define the omega by using the equation that we derived in the previous slide, and if we plot the omega line, then we can obtain this omega is equal to omega 0. Omega is the equation of the line. So when we plot the omega, we can see the maximally we can see the projection line that maximally separate these two data sets. So let's see some histogram. So these scatter plot are our original data, and when you project these data onto this omega that we found in the last slide, we can see that two histograms are well maximally separate like this. So we can clearly see the two classes C0 and C1. And we can see that within each data class, data are well tightened. And if we choose a different omega like this, and when we plot this histogram onto projection onto this line, then we can see many of data are overlapped here. So from that we cannot distinguish two classes. And also these data are widely spread, so this is not an ideal case. And also if we choose a different omega like this, here we still observe this overlapping region, and also data are mostly spread, so this is also not a good case. And finally, let's implement these FTA algorithms in scikit-learn. So as we learned last time, the scikit-learn is very useful for implementing various algorithms. So here from scikit-learn, let's import discriminant analysis. And let's define our classification model CLF as variable for this. So here from the class of discriminant analysis, let's implement a linear discriminant analysis. So here we use LDA, and if you just use the comment for CLF.fit, then from that you can directly find the LDA projection line. So from that we can project this data that preserve the original class information. And as the last topic and last algorithm, let's learn about a singular value decomposition, or also called SVD. Before talking about in detail about SVD, let's talk about a linear mapping of the matrix. So in the first lecture, in the linear algebra class, we have learned that matrix A it can be understood as a linear transformation, and which is just nothing but the summation of some rotation and stretch or compress. So here, let's say we have two vectors, v1 and v2, in the original domain A, and when you multiply these vectors to like to the x, then our original vector can be transformed like this. So here, this one is sigma 2 u2, and this one is sigma 1 and u1. So by multiplying this v1 vector using a matrix, the results are av1, which is equal to sigma 1 and u1. And when you multiply the v2 vector with matrix A, the result of v2 is equal to sigma 2 u2. So from that, we can understand that the matrix A is just linear transformation, and this one is the two steps of rotation and stretch or compress. So from the geometry of linear maps, an extremely important fact is that every matrix in the A domain, every matrix maps the unit ball to an ellipsoid. So here, let's say this one is just the same as what we discussed earlier. So for any vectors in the unit ball Rn space, any vector can be transformed to an ellipsoid. So here S is equal to S vector, S set. So based on this, let's learn in detail about singular value decompositions. Before knowing about singular value decomposition, we should know about the singular values and singular vectors. And actually, this one is very similar to like eigenvector, eigenvalue, and eigenvector. But the difference is for the singular value and singular vector, that is for a more general case that for working at the non-square case. But when we learn about the eigenvalues and eigenvector, the vector should be the square matrix n by n. So when the matrix is the square matrix, we can calculate eigenvalues and eigenvector. But when the vector has the rectangular shapes, that means m is not equal to n, then we can consider singular values and singular vectors. So the numbers sigma 1 and sigma r, sigma n, sigma 1, sigma 2, sigma n are called as singular values of A by convention, and sigma I should be larger than 0. And the vectors u1, u2, un are unit vectors along the principal semi-axis of AS, and the vectors v1, v2, and vn are the preimages of the principal semi-axis, defined so that avi is equal to sigma I ui. So by the definition, A is the matrix which has the same of m times n, and the vi is the vector, so its size should be the n times 1, and sigma I should be the scalar value, and ui should be the vectors that has this shape of m times n, m times 1. So here A is equal to m times n, and the vi is equal to n times 1, and sigma I is the scalar values, so singular values, that means the scalar values, and ui is the m times 1 size. And from the previous slides, we have learned that the
vector matrix multiplication, matrix vector multiplication can be understood as the rotation and compress or stretch. So by multiplying the A matrix with the unit vector Vi, this can be transformed to the vectors with sigma 1 u1 or sigma 2 u2. So here, by just rewriting these V1 and U1 using the vector matrix, so here this one is the can be understood as the column vectors of the V1, and this one is also the column vectors of U1 and U2 to UR. So by multiplying this, and when you rewrite this scalar value to diagonal matrix, this relation can be represented as the vector form by combining this. So AV is equal to U sigma. So by using it, let's consider singular value decomposition. And especially for this case, let's think about A matrix as a thin matrix. That means A matrix has a skinny and full length. That means A matrix that has M times N. But here, skinny means M should be larger than N. So the A matrix has more columns, more rows compared to the number of columns. And full length means R is equal to N. So that is our special case. And for that, we know that M has A matrix has the size of M times N, and the V matrix has the size of N times 1. And sigma I is the singular value, so this one is the scalar. And UI is the matrix that has the M times 1 size. So here, by rewriting these orthogonal matrix, orthogonal unit vectors, so U1 to UN are orthogonal unit vector that satisfies the UI times the inner product between UI and UJ is equal to 0 or 1, and when I is not the same as J, it would be the 0, and when I is equal to I is equal to J, then its inner product would be the 1. So by rewriting this U vector and by rewriting sigma vector that has the only diagonal term with our single values, and V is also the orthogonal unit vector. And from the linear algebra, we know that for the orthogonal unit vector, orthogonal unit vectors satisfy this condition, so that so in that case, U transpose, let's say, U transpose U is equal to identity matrix. So from that, U transpose is just the same as U inverse. So from the previous slide, we constructed the matrix information that AV is equal to U times sigma. So from that, we can rewrite the A is equal to U sigma V transpose, because we know that V transpose V is equal to V times V transpose I. So from that, we can construct the A matrix as equal to U times sigma V transpose. So here A has the matrix of M times N, and the N matrix has the also M times N matrix, and the sigma has only diagonal term with the size of N times N, and the V transpose is also the matrix of N times N. Then how can you interpret the meaning of the SVD in mathematical way? As we learned, the A matrix in the SVD, A matrix can be decomposed like
like U times sigma times V transpose, where A matrix has the where A matrix is the matrix. And we know that when we multiply the vector to matrix, it can be understood as a linear mapping. So here, when we multiply the x vector, it's kind of a linear mapping. We transpose x first. So it's first we need to rotate. So from that, we transpose x is just nothing but the rotation by Vt. And here we know that V matrix is orthogonal matrix, so that means its inner product between the two vectors are simply can be written as 0 or 1, depending on when the I is equal to j. I is equal to j, its inner product is 1. So that means v vector is the unit vector. So when you multiply some vectors to unit vector, its magnitude will not be changed. So it's just rotating itself. So we do not compress or we do not stretch the vector size, but we just rotate the vector by V transpose. And then we multiply this sigma, and sigma is just composed of our singular value. So the diagonal components are just our singular values. So for that, it can be understood as diagonal scaling by sigma 1. So we just stretch or compress the size by sigma 1. And then we need to rotate by the u vector. So similar to the v vector, u vector is also an orthogonal matrix. So it's composed of unit vectors. So it just rotate by u. So this one is so by decomposing the A matrix to SVD, SVD decomposes the linear mapping, just rotating, diagonal scaling, and rotate. So firstly, we need to rotate by V transpose, and we need to scale diagonally by sigma I, and then we need to rotate by U. And here you should know that unlike the eigen decomposition, input and output directions can be different. So here, from the SVD decomposition, AVI is equal to lambda I VI. So in the diagonal matrix, we have the same input and output directions. But here, from the SVD, the relations can be written as AIVI is equal to sigma IUI. So the output has different dimensions because VI has the size of, let's say, size of n by 1, and UI has the size of m by 1. So for any matrix A that has the size of m times n, the matrix can be decomposed by using singular value decomposition, where U sigma V transpose. And for a specific case where symmetric and positive definite matrix A, which has the size of n by n, so it has the symmetric and positive definite matrix, then A can be decomposed like S lambda S inverse. And here, because S is also orthogonal matrix, so it can be written as S lambda S transpose. And here, especially, we call it as eigenvectors and eigenvalues. Then the question is, how can you find U and V vectors? So here, by using singular decomposition, any matrix A can be decomposed like U sigma and V transpose. So for by finding these singular vectors and singular values, we can decompose any vectors. Then and from A, which has skinny and full length, we can construct two positive definite symmetric matrix by multiplying A transpose and also A transpose A. And here, as we know that A has
has the size of m by n. The A transpose is just the size of the m by m, and for the case of A transpose as A has the size of n by n. So we're gonna have two positive definite symmetric matrices. And by using the fact that any real symmetric and positive definite matrix has a eigen decomposition, so here by using the eigenvectors and eigenvalues, any matrix can be decomposed like eigenvectors. So by using these two facts, when we just rewrite the AA transpose, it's nothing but the U. And here, by calculating AA transpose, you can calculate the eigenvalues of AA transpose. You can compute the U vector and also sigma. And here, by calculating A transpose A, you can calculate the eigenvectors of V. So by using this, you can calculate U and V and also sigma. So that's all. So that's it. By doing so, you can find the U, V, and sigma matrix. So by using these three matrices, you can decompose any matrix of A. So let's implement this in Python code. So for that, what we need to do is just firstly define some matrix, and what we need to do is just calculating A transpose, the eigenvalues of A transpose A, and also eigenvalues and eigenvectors of A transpose. So that's it. So by doing so, you can calculate the eigenvalues and eigenvectors, and here also eigenvalues and eigenvectors. So by doing so, what we are doing is just exactly the same as calculating V and U and sigma vectors. So by using these, by using U and sigma and V transpose, you can decompose the original A matrix. So that's all for the SVD. So then let's learn the relationship between PCA and SVD. So when you calculate the SVD, we need to calculate A transpose A and A transpose. So by using these two symmetric matrices, you're gonna calculate V and U. And here, when you think about when the X and the A is equal to X, this one is nothing but the covariance matrix. Because S is equal to 1 over M times X transpose X. So here, A transpose S is nothing but the calculating covariance matrix. And by calculating the eigenvalues and eigenvectors of A transpose A, you can calculate the V and V transpose. So here, by calculating the find the eigenvectors of the covariance matrix, you can calculate the V, right? And especially but when in the previous lecture, we have learned that PCA is just calculating the eigenvectors of the covariance matrix. So the columns of V are just nothing but the principal axis. So from that, we can conclude that among the two vectors of two matrices of symmetric matrix, by calculating A transpose A in the singular value decomposition to calculate the V matrix, you are just doing some PCA. So PCA and SVD are closely related. So here, this one is the conclusion. So in the PCA, what we are doing is just calculating the matrix, the eigenvalue decomposition of the covariance matrix. So here, this one is nothing but exactly the same as the calculating SVD when you calculate A transpose A. So finally, by using this, let's do some dimensional reduction using SVD. So as you discussed earlier, all the A matrix, the multiplication of vector and matrix can be understood as the linear mapping. So by using singular decomposition here, let's say let's consider only two-dimensional case. And by using the singular decomposition, A matrix can be decomposed using U sigma V transpose X. And in general, for more general cases, A matrix can be also understood as U R sigma R V R transpose. And here, by selecting, similar to the PCA algorithm, by selecting some high rank or high singular values, let's say from only select K important principal axis, or not say principal axis, just K important rank, which is smaller than the R. This can be approximated using UK sigma K VK transpose. So by using this value, we can reconstruct the A matrix that is similar to a let's say A hat, and this one is only reconstructed from only K singular vector matrix. So here, this is the dimensionally reduction using SVD. So let me rewrite the mathematical way of low-rank approximation or dimensionally reduction using singular value decomposition. And as we learned from the previous slide, the matrix A can be decomposed using U, sigma, and V transpose. And here, A has the size of A, so the matrix form can be understood as like this. So A matrix has the size of M times N, but here we will consider a full rank system, so we have a rank R. And A is the U matrix has the form. U matrix has the form of also the size of M times R, and the sigma vector has this sigma vector is the singular composed of singular values, and the matrix V transpose is also the R times R. And here, by selecting only K important singular vectors and K important singular values, we can reduce the dimensional reduction. And by using this fact, this can be used for image approximation using low dimension. So here, let's approximate the original images by using singular value decomposition. And the low rank approximation is just nothing but a UK, which is just UK. Let's say this is UK matrix, and this one is sigma K, and this one is V transpose K matrix, and this one is composed of when K is smaller than R, this one is the this one is just nothing but sigma I UI VI transpose. And let's compress these images like this. And let's say for these images that has, let's say 1000 by 1000, by using this matrix, our U matrix, and by approximating images with rank only 20, our U matrix we're gonna have the size of 1000 times 20, and sigma we're gonna have 20 times 20, and V transpose will have 20 by 100 to 20 by 1000. So by using these three matrices, you can approximate these original images to the to the compressed images, but at the same time, still it contains the high quality images compared to original images. So here, for that, we can reconstruct these images by using only row rank. This is one of the examples that SVD can be applied. And for SVD, let's implement this in Python code. So what you need to do is first you need to import some images, and then you can use the SVD algorithm in NumPy.linear algebra class. So here at np.linear algebra some SVD, you can just decompose singular value decomposition, and by doing so you can calculate U, S, and V transpose. So here, by taking this matrix as matrix, and you're gonna get this result like this. And from that, let's approximate these images with low rank where R is equal to 20. So let's first define the K is equal to 20, and let's just select some highest K values for that. So for highest K value, let's take the first 20 eigenvalues and eigenvectors, and by multiplying this again, you can obtain the A hat, which is approximated images like this. So this one is very simple example that we can use SVD in practical applications. Yeah, so today we have learned basic 2 algorithms of dimensional reduction. The first one is FDA, and the second one is SVD. So yeah, that's very important algorithms. So yeah, that's it for today's lecture. And thank you for your listening.